In the constellation Scutum, nearly 6,000 light-years from Earth, a red monster pulses with the power to swallow worlds. UY Scuti stretches 1,700 times wider than our Sun, a stellar giant so massive that if you placed it where our Sun sits, its burning surface would extend past Mars and into the asteroid belt. But this cosmic leviathan harbors a terrifying secret. We will journey to witness a star that devours light itself, explore the nuclear fires that forge death in stellar cores, and discover explosions so violent they outshine entire galaxies for months. Like and subscribe to join us on this voyage through cosmic destruction. UY Scuti has begun its final death spiral, and when giants this large die, they take entire star systems with them. Prepare yourselves. We begin. UY Scuti makes our Sun look like a grain of sand next to a basketball. This red supergiant burns in the constellation Scutum, pulsing with a heartbeat that lasts 2 years. Every time it breathes, the star expands and contracts across distances that would take light over 8 minutes to cross. Picture this. If UY Scuti replaced our Sun tomorrow, Earth would already be inside the star. Mars would be inside the star. The asteroid belt would be drowning in stellar plasma hotter than any forge humans have ever imagined. Only Jupiter might escape the star's outer layers, orbiting just beyond a surface that glows like molten copper. But size tells only part of this monster's story. UY Scuti weighs just 30 times more than our Sun, yet stretches 1,700 times wider. Think of it like a soap bubble the size of a football stadium, incredibly vast, but surprisingly light for its enormous volume. This strange relationship between mass and size reveals the star's terrifying secret. The star burns through fuel so fast that it has already consumed most of its hydrogen in just 10 million years. Our Sun, by comparison, has been burning steadily for over 4 billion years and has another 5 billion to go. UY Scuti lives like a cosmic sprinter, burning bright and dying young. As the star runs out of fuel, gravity begins winning its eternal battle against the nuclear fires in the core. The outer layers start to puff outward, creating the enormous size we see today. But this expansion signals something sinister. UY Scuti has entered its death phase, and for stars, this massive death means something far more violent than a peaceful fade. The star's surface temperature has dropped to just 3,000 degrees, cooler than many smaller stars. This is why it glows red, instead of the yellow-white of our Sun. The cooler temperature might seem less threatening, but it actually marks the beginning of a countdown to cosmic catastrophe. Deep in the star's core, fusion continues at a frantic pace. Hydrogen burns into helium, helium fuses into carbon, carbon transforms into oxygen and silicon. Each new element requires higher temperatures and pressures to fuse, pushing the star's internal furnace to ever more extreme conditions. UY Scuti sits nearly 10,000 light-years away, far enough that its eventual demise poses no direct threat to Earth. But even at this vast distance, when this monster finally dies, it will briefly outshine every other star in our galaxy's sky. The explosion will be visible during the day, casting shadows on Earth despite the incredible distance. What happens next makes UY Scuti's enormous size seem almost insignificant. The nuclear furnace at UY Scuti's heart faces an enemy that no amount of fuel can defeat. Physics itself has set a trap that will destroy the star, and the countdown has already begun. For millions of years, UY Scuti has burned hydrogen into helium in its core, creating the outward pressure needed to fight gravity's inward pull. But hydrogen fuel doesn't last forever, especially when you're burning through it 1,000,000 times faster than our Sun. When the core finally runs out of hydrogen, the star begins a deadly game of nuclear desperation. Think of it like a campfire running out of kindling. To keep the flames alive, you throw on bigger logs, then chairs, then pieces of the house itself. UY Scuti does something similar, but with atomic nuclei. As hydrogen disappears, the core contracts and heats up until it becomes hot enough to fuse helium into carbon. This helium burning releases even more energy than hydrogen fusion, causing the star to brighten and expand further. The outer layers puff outward like a balloon being inflated, reaching the enormous size that makes UY Scuti the largest known star. But helium burns much faster than hydrogen, lasting only about 1 million years instead of 10 million. When helium runs out, the core contracts again, heating up until carbon begins to fuse into oxygen and neon. Then oxygen fuses into silicon. Each stage burns hotter, faster, and more violently than the last. The star becomes like a runaway nuclear reactor, desperately trying to maintain the energy output needed to support its own massive weight. Silicon fusion produces iron, and here the star meets its doom. Iron cannot be fused into heavier elements without actually consuming energy instead of releasing it. It's like trying to burn ashes. No matter how hot your fire gets, ashes won't give you more fuel. When the core fills with iron, nuclear fusion stops completely. Without the outward pressure from fusion, gravity wins its billion-year battle in less than 1 second. The core, which moments before was larger than Earth, collapses down to a ball barely 12 miles across. The collapse happens so fast that the outer layers don't even know what's happening yet. The core becomes so dense that a teaspoon of its material would weigh as much as Mount Everest. Electrons get crushed into protons, forming neutrons and releasing floods of ghostly particles called neutrinos. In 1 second, the collapsing core creates more neutrinos than our Sun will produce in its entire lifetime. But this is just the beginning of UY Scuti's death throes. In less time than it takes to blink, UY Scuti's core becomes the densest object in the known universe. What happens next unleashes forces so violent they will be visible from other galaxies. Imagine trying to squeeze all the people on Earth into a space the size of a marble. The core collapse of UY Scuti is far more extreme. The star's entire iron core, weighing more than our Sun, crushes down to a sphere just 12 miles wide. The density becomes so incredible that atomic structure itself breaks down. Electrons, which normally orbit atomic nuclei like planets around a star, get forced into the protons in the nucleus. This creates neutrons and releases tremendous amounts of energy in the form of neutrinos, particles so ghostly they can pass through entire planets without hitting anything. But in the ultra-dense core, even neutrinos struggle to escape. The collapse happens faster than sound can travel through the star. While the core implodes at 30,000 miles per second, the outer layers continue falling inward, completely unaware that the core has already stopped. It's like a massive traffic jam in space, with layers of stellar material piling up at incredible speeds. When the infalling material finally slams into the ultra-dense core, it's like dropping a bowling ball onto concrete. The material bounces back, creating a shockwave that races outward through the star at 10,000 miles per second. This shockwave carries more energy than our Sun will produce in its entire 10 billion year lifetime. But here's where things get even stranger. The shockwave stalls about halfway through the star, losing energy as it tries to push through the incredibly dense material. For several hours, the fate of UY Scuti hangs in the balance. Will the shockwave break through and explode the star? Or will it fail and let the entire star collapse into a black hole? The answer comes from those ghostly neutrinos trapped in the core. Though most neutrinos pass through matter easily, the core has become so dense that some of them finally interact with the surrounding material. Just 1% of the neutrino energy gets deposited in the stalled shockwave, but that's enough to revive it. The shockwave roars back to life, ripping through the star's outer layers like a cosmic wrecking ball. When it finally breaks through the surface, UY Scuti will become visible from Earth even in broad daylight. The explosion will shine with the brightness of 5 billion suns, announcing the violent death of the galaxy's largest star. The neutrinos, meanwhile, escape at the speed of light, carrying 99% of the explosion's energy into space. If you could see neutrinos with your eyes, the dying star would appear brighter than anything in the universe for about 10 seconds. But the real show is just beginning. The shockwave from UY Scuti's death carries enough energy to power every device on Earth for longer than the universe has existed. When it breaks free from the star's surface, it will create a light show visible from neighboring galaxies. As the shockwave tears through UY Scuti's outer layers, It heats the stellar material to temperatures of 100 million degrees, 6 times hotter than the Sun's core. At these extreme temperatures, the expanding gas glows brighter than entire star clusters, creating what astronomers call a supernova. The explosion hurls the star's outer layers into space at speeds of 20,000 miles per second. That's fast enough to circle Earth in just 13 minutes. The expanding shell of superheated gas and plasma grows larger than our entire solar system within days, carrying with it all the elements that UY Scuti created during its lifetime. Think of it like the ultimate cosmic recycling program. Every atom of carbon in your body, every molecule of oxygen you breathe, every fleck of iron in your blood was forged in the nuclear furnace of a dying star. UY Scuti's explosion will scatter these life-giving elements across hundreds of light-years of space, seeding future generations of stars and planets. But the explosion does more than just scatter existing elements. The incredible energies involved actually create new atomic nuclei that cannot form anywhere else in the universe. Elements heavier than iron, including silver, gold, platinum, and uranium, only exist because of supernova explosions like the one that will eventually destroy UY Scuti. The Shockwave acts like a cosmic particle accelerator, smashing atomic nuclei together with such force that they stick together to form these heavy elements. In just a few seconds, the explosion creates more gold than exists in Earth's entire crust. The platinum in your jewelry, the silver in your electronics, the uranium that powers nuclear reactors, all of it came from stellar explosions, just like this one. For months after the initial explosion, UY Scuti will continue to brighten. The expanding shockwave becomes transparent to light, revealing a glowing ball of radioactive elements in the center. These radioactive atoms decay rapidly, releasing energy that keeps the supernova shining long after the initial explosion fades. The supernova will be so bright that it would be visible from Earth even during the day, appearing as a brilliant new star in the constellation Scutum. Ancient civilizations would have seen it as an omen, unaware that they were witnessing the death of the largest star in the galaxy. At its peak brightness, the explosion will outshine the combined light of every other star in the Milky Way. For a brief moment, UY Scuti's death will make our entire galaxy appear twice as bright to any aliens observing from distant universe. Yet, even this incredible display pales compared to what remains behind. What's left after UY Scuti explodes will be stranger than any science fiction writer ever imagined. In the center of the expanding explosion, a remnant forms that makes a mockery of everything we think we know about matter. The ultra-dense core that triggered the explosion doesn't disappear. Instead, it becomes something called a neutron star, an object so bizarre that astronomers initially refused to believe such things could exist. Imagine crushing the entire mass of our Sun down to the size of Manhattan. The resulting object would have the same density as UY Scuti's corpse. A neutron star is exactly what its name suggests. A star made almost entirely of neutrons. The extreme gravity has crushed protons and electrons together, creating the largest atomic nucleus in the universe. The entire star is essentially one giant atom, 12 miles wide, but containing more matter than our Sun. The surface gravity on this neutron star would be 200 billion times stronger than Earth's gravity. If you could somehow stand on its surface, you would weigh as much as Mount Everest. A marshmallow dropped from waist height would hit the ground with the force of an atomic bomb. But gravity is just the beginning of this object's strangeness. The neutron star spins incredibly fast, rotating hundreds of times per second. It's like a cosmic blender, whipping around faster than helicopter blades. This rapid rotation creates magnetic fields 1 trillion times stronger than Earth's magnetic field, strong enough to strip electrons from atoms thousands of miles away. The neutron star's magnetic field channels particles into narrow beams that sweep across space like lighthouse beams. If one of these beams points toward Earth, we detect rapid pulses of radio waves, earning these objects the nickname pulsars. The pulses arrive with clockwork precision, more accurate than the best atomic clocks humans have ever built. The surface of the neutron star is a crystalline landscape harder than diamond, but under pressures that would instantly vaporize any material found on Earth. The atmosphere is just a few inches thick, and made of hydrogen and helium heated to millions of degrees. Any mountains on the surface would be less than an inch tall. The incredible gravity allows no significant bumps or valleys. Beneath the crust lies matter in states that cannot be recreated in any laboratory on Earth. The neutrons may break down into even stranger particles called quarks, creating a liquid more exotic than anything in our everyday experience. Scientists call this theoretical substance quark soup. The neutron star contains more mass than our Sun, but you could drive across its entire diameter in less than an hour. Space and time become warped around such a dense object, bending light and slowing down time itself. A clock on the neutron star's surface would run noticeably slower than a clock on Earth. But if UY Scuti's core is even more massive, something far stranger happens. If UY Scuti's core weighs more than about 3 times our Sun's mass, not even neutron degeneracy pressure can stop the collapse. What forms next is an object so extreme that it breaks the very fabric of reality. Nothing in the universe can stop this final collapse. The core continues shrinking past the neutron star stage, crushing matter into a mathematical point of infinite density. Space and time themselves become twisted beyond recognition, creating what physicists call a black hole. Though hole is misleading, since it's actually the most concentrated mass possible. At the center lies something called a singularity, where all known laws of physics simply stop working. It's a place where density becomes infinite, and space-time curvature becomes so extreme that our mathematical equations literally divide by 0. No one knows what really exists at a singularity because the mathematics breaks down completely. The black hole creates an invisible boundary in space called the event horizon. Nothing that crosses this boundary can ever escape, not even light itself. The event horizon forms like a cosmic trapdoor. You can fall in, but you can never climb back out. For a black hole with the mass of UY Scuti's core, this point of no return would have a diameter of about 180 miles. Think of space-time like a stretched rubber sheet, with objects creating dips and curves in the fabric. A black hole punches a bottomless hole through the sheet, creating a gravitational well so deep that not even light has enough energy to climb out. From the outside, anything falling toward the black hole appears to slow down and freeze at the event horizon, its light becoming redder and dimmer until it fades from view. But the infalling object experiences something completely different. From its perspective, it falls through the event horizon in normal time and continues toward the singularity. However, the tidal forces, the difference in gravitational pull between head and feet, stretch the object like taffy in a process astronomers grimly call spaghettification. Near the event horizon, time itself becomes warped. A clock falling toward the black hole would run slower and slower compared to a clock far away. At the event horizon, time dilation becomes infinite. Time literally stops from the perspective of a distant observer. This creates a frozen moment that lasts forever, preserved at the boundary between space and oblivion. The black hole's gravity is so intense that it affects light passing nearby, bending the paths of photons like a cosmic lens. This gravitational lensing allows the black hole to focus light from objects behind it, creating multiple distorted images of the same star or galaxy. The black hole acts like a funhouse mirror on a cosmic scale. If you could somehow orbit close to the black hole without falling in, you would experience time dilation effects straight out of science fiction. A few hours near the event horizon would equal years or decades for observers far away. You could literally travel into the future by taking a trip around a black hole. But even black holes aren't the most violent things UY Scuti's death might create. If UY Scuti spins rapidly as it dies, its black hole remnant could unleash the most powerful, sustained explosion in the universe. What emerges makes ordinary supernovas look like birthday candles. When a rapidly rotating massive star collapses into a black hole, something extraordinary happens. The conservation of angular momentum causes the black hole to spin incredibly fast, creating a cosmic dynamo that generates magnetic fields millions of times stronger than anything else in the galaxy. These magnetic fields channel matter and energy into narrow jets that shoot out from the black hole's poles at nearly the speed of light. These relativistic jets are like cosmic blowtorches stretching across thousands of light years. They carry more energy than our sun will produce in its entire lifetime, focused into beams narrower than our solar system. If you stood in the path of one of these jets, you would be exposed to radiation levels millions of times more intense than standing next to a nuclear reactor. The jets create what astronomers call a hypernova, an explosion at least 10 times brighter than an ordinary supernova. While a regular supernova might outshine its host galaxy for a few weeks, a hypernova can remain brighter than billions of stars for months. It's the difference between a flashlight and a searchlight visible from space. The hypernova generates a gamma-ray burst, the most energetic explosion known to occur in the universe since the Big Bang itself. In just 10 seconds, the gamma-ray burst releases more energy than our sun will produce over its entire 10 billion-year lifetime. If a gamma-ray burst occurred in our galaxy and pointed toward Earth, it would deliver radiation equivalent to bringing the surface of the sun down to Earth's atmosphere. Think of a gamma-ray burst as nature's ultimate laser pointer. The energy that would normally spread out in all directions gets focused into two narrow cones, concentrating the destructive power like sunlight through a magnifying glass. This focusing effect makes the explosion visible from billions of light years away, allowing astronomers to detect hypernovas from across the observable universe. The gamma rays themselves are photons with energies millions of times higher than visible light. A single gamma ray photon carries as much energy as an entire visible light wave. When these high-energy photons hit Earth's atmosphere, they create cascades of secondary particles, turning our sky into a cosmic particle accelerator. A nearby gamma-ray burst could strip away Earth's ozone layer in seconds, exposing the surface to deadly ultraviolet radiation from the sun. The burst would also create nitrogen oxides in the atmosphere, generating a brown smog that would block sunlight and trigger a global ice age. Mass extinctions in Earth's past may have been caused by gamma-ray bursts from distant hypernovas. The jets from UY Scuti's potential hypernova would drill through space for thousands of years, creating hot bubbles of gas larger than entire star systems. These cosmic cavities would glow with X-ray light, marking the grave of the largest star in the galaxy with a monument visible from other galaxies. But the destruction doesn't end with the initial explosion. The expanding shell of debris from UY Scuti's explosion will travel through space for millions of years, bulldozing through interstellar gas and triggering the birth of countless new stars. Death and creation become two sides of the same cosmic coin. The supernova Shockwave races outward at 20,000 miles per second, but it doesn't travel through empty space. The region between stars contains thin clouds of hydrogen gas, dust particles, and the remnants of previous stellar explosions. When UY Scuti's shockwave hits these clouds, it compresses them like a cosmic snowplow, creating conditions perfect for star formation. Think of it like throwing a stone into a still pond. The ripples spread outward in expanding circles, but instead of water waves, we're talking about waves of superheated plasma carrying the mass of entire planets. These expanding shells of debris are called supernova remnants, and they can grow larger than our entire solar system. The shockwave heats the surrounding gas to millions of degrees, creating a glowing bubble visible in X-ray telescopes. This superhot gas expands and cools over thousands of years, eventually mixing with the interstellar medium and dispersing the heavy elements created during UY Scuti's lifetime. The carbon, oxygen, silicon, and iron forged in the star's core get scattered across hundreds of light years. As the shockwave plows through dense molecular clouds, it compresses the gas until gravity takes over and begins forming new stars. The death of UY Scuti could trigger the birth of thousands of new stars over the next few million years. Some of these new stars will have planets, and some of those planets might develop life using the elements scattered by UY Scuti's explosion. The supernova remnant creates a vast cavity in the interstellar medium, like a soap bubble blown in cosmic fog. These bubbles can be hundreds of light years across and remain visible for millions of years. Our own solar system sits inside one of these ancient supernova bubbles, created by massive stars that exploded millions of years ago. The expanding shockwave also acts like a cosmic particle accelerator, speeding up protons and electrons to nearly the speed of light. These high-energy particles become cosmic rays that travel throughout the galaxy, occasionally hitting Earth's atmosphere and creating the northern and southern lights. Every cosmic ray that strikes Earth's atmosphere may have been accelerated by a supernova explosion like the one that will eventually destroy UY Scuti. The energy from the explosion doesn't just create new stars, it can also destroy them. If UY Scuti exploded close enough to a planetary system, the intense radiation and shockwave could strip away planetary atmospheres and sterilize any worlds that might harbor life. The explosion becomes an agent of both creation and destruction on a galactic scale. Over millions of years, the supernova remnant will fade and disperse, but its effects will last for billions of years. The heavy elements scattered by the explosion will be incorporated into new generations of stars and planets, ensuring that UY Scuti's legacy continues long after the star itself has vanished. Yet this is just one star among billions. Our galaxy is littered with the corpses of massive stars, each one a testament to the violent deaths that have shaped the Milky Way over billions of years. UY Scuti will soon join this cosmic cemetery. The Milky Way contains an estimated 100 billion stars, but most of them are small, long-lived red dwarfs that burn for trillions of years. Only about 1% of stars are massive enough to explode as supernovas, but their impact on galactic evolution is enormous. These stellar giants live fast, burn bright, and die young, enriching the galaxy with heavy elements essential for planets and life. Astronomers estimate that a supernova occurs in the Milky Way roughly once every 50 years. That means, in the 4.5 billion years since Earth formed, nearly 100 million massive stars have exploded in our galaxy. Each explosion scattered elements into space, gradually increasing the concentration of heavy elements available for new star and planet formation. The evidence of these ancient explosions surrounds us. The Crab Nebula marks the site of a supernova that Chinese astronomers recorded in the year 1054. The explosion was so bright that it remained visible during the day for 23 days. At the center of the expanding gas cloud sits a neutron star spinning 30 times per second, the compressed core of the original massive star. Closer to home, the Vela supernova remnant spans 8 degrees across the southern sky, 16 times wider than the full moon. This explosion occurred about 11,000 years ago and was so close that it may have been brighter than the full moon for several weeks. The shockwave has carved out an enormous cavity in the local interstellar medium, and we're still inside the bubble it created. Our solar system itself shows signs of being influenced by ancient supernovas. The local bubble, a region of hot, thin gas surrounding our solar system, was likely created by a series of supernova explosions from a group of massive stars that lived and died over the past 10 million years. We're essentially living inside a supernova remnant. Some scientists think that nearby supernova explosions may have influenced the evolution of life on Earth. The increased cosmic ray flux from these explosions could have triggered climate changes or genetic mutations that affected the course of biological evolution. The iron-60 isotope found in deep-sea sediments suggests that multiple supernovas occurred within 300 light-years of Earth over the past few million years. The galaxy contains roughly 100 million neutron stars and 10 million black holes, the compressed remnants of all those exploded massive stars. Most of these objects are invisible, detectable only when they interact with nearby matter or companions. But occasionally, we catch glimpses of their extreme properties through radio pulses, X-ray emissions, or gravitational wave detections. UY Scuti will eventually add its own corpse to this stellar graveyard. Whether it becomes a neutron star or black hole, it will remain as a permanent reminder of the largest star in the galaxy, long after its brilliant light has faded and its heavy elements have been scattered to the cosmic winds. But the cycle of stellar death and rebirth continues. Every atom in your body was forged in the nuclear furnace of a dying star, scattered through space by supernova explosions, and eventually incorporated into the planet you call home. UY Scuti's death will continue this cosmic cycle of renewal. When UY Scuti explodes, it will scatter approximately 25 times the mass of our Sun into the surrounding space. This debris contains all the elements the star created during its lifetime. carbon from helium fusion, oxygen from carbon burning, silicon from oxygen fusion, and iron from the final stages of nuclear burning. The explosion will also create elements heavier than iron through rapid neutron capture processes that only occur during supernovas. Think of each supernova as a cosmic seed dispersal, spreading the ingredients for future worlds across vast distances. The expanding shockwave will carry these elements hundreds of light years from the explosion site, mixing them with existing interstellar gas and dust. Over millions of years, this enriched material will be incorporated into new molecular clouds where the next generation of stars will form. The carbon scattered by UY Scuti's explosion could eventually become part of organic molecules in distant worlds. The oxygen will form water and rocky minerals. The silicon will create the basic building blocks of planetary crusts. The iron will sink to planetary cores, generating magnetic fields that protect surface life from harmful radiation. Every element heavier than hydrogen and helium in your body came from stellar explosions just like this one. But the enrichment process is gradual. When the universe was young, it contained only hydrogen and helium created in the Big Bang. The first generation of stars had no heavy elements to work with, so they couldn't form rocky planets or complex chemistry. Only after these first massive stars lived and died could the universe begin creating Earth-like worlds capable of supporting life as we know it. Our solar system formed from a molecular cloud that had already been enriched by billions of years of stellar evolution. The heavy elements in Earth's rocks, the iron in your blood, the calcium in your bones, all of it was created in the cores of massive stars and scattered by supernova explosions. We are literally made of star stuff, the recycled remnants of ancient stellar furnaces. UY Scuti represents the continuing evolution of our galaxy's chemical composition. As one of the largest stars ever found, its death will scatter more heavy elements into space than dozens of smaller supernovas. These elements will remain in the interstellar medium for millions of years, waiting to be incorporated into future generations of stars and planets. Some of the material from UY Scuti's explosion may eventually find its way into solar systems that won't form for billions of years. Planets that don't yet exist will be built from atoms forged in UY Scuti's core. Life forms that we can't imagine may one day depend on the carbon, oxygen, and other elements created by this dying giant. The death of UY Scuti will ensure that the cosmic cycle of stellar evolution continues. From destruction comes creation. From endings come new beginnings. The largest star in the galaxy will live on not as a single object, but as countless atoms scattered throughout space, carrying the potential for future worlds and future life among the stars. And somewhere in our galaxy, an even larger star may already be growing. While UY Scuti holds the current record as the largest known star, the universe almost certainly hides even bigger monsters waiting to be discovered. The search for stellar giants has only just begun. Astronomers have surveyed less than 1% of the stars in our galaxy, and the Milky Way itself contains over 100 billion stars. Most of these remain completely unknown to us, hidden behind clouds of interstellar dust, or simply too faint and distant for our current telescopes to detect. Among these unexplored stellar populations, there could be red supergiants that make UY Scuti look small. The problem with finding the largest stars is that they tend to be the most difficult to observe. Red supergiants like UY Scuti are often shrouded in thick clouds of dust that they've ejected from their surfaces. This dust absorbs visible light, making the stars appear much dimmer than they actually are. Many potential record holders may be hiding in plain sight, invisible to optical telescopes but glowing brightly in infrared light. Consider the star-forming regions in distant galaxies, where conditions might allow for the formation of stars even more massive than anything we've seen in the Milky Way. The Magellanic Clouds, two small galaxies orbiting our own, already host several contenders for the size record. But we've barely begun to survey the stellar populations in galaxies millions of light years away. The early universe contained different conditions that might have allowed for the formation of truly gigantic stars. The first generation of stars, called Population 3 stars, formed from pure hydrogen and helium with no heavy elements to help them cool and fragment during formation. Some theoretical models suggest these primordial giants could have grown to thousands of times the mass of our Sun before collapsing into black holes. Even in our local cosmic neighborhood, new discoveries continue to surprise astronomers. In 2021, researchers identified a star called Stephenson 2 DFK1 that might be even larger than UY Scuti. Early measurements suggested it could be over 2,000 times wider than our Sun, though the distance uncertainty makes this difficult to confirm. The James Webb Space Telescope, with its unprecedented infrared vision, is already revealing hidden populations of massive stars in distant galaxies. Its ability to see through dust clouds that hide optical light means we're likely to discover many more stellar giants in the coming years. Each new observation could potentially dethrone UY Scuti from its position as the largest known star. Variable stars like UY Scuti also complicate the search for size records. These giants pulsate over periods of months or years, expanding and contracting by significant amounts. A star might hold the size record during its maximum expansion phase, but shrink below the current record holder during contraction. We may need decades of monitoring to determine which star truly deserves the title. The universe has had over 13 billion years to create stellar monsters, and we've only been looking for them seriously for a few decades. The odds strongly favor the existence of stars that dwarf even UY Scuti's impressive dimensions. But size isn't the only way to measure stellar extremes. While UY Scuti wins the contest for sheer size, other stars pack far more mass into smaller spaces, burning with intensities that make our Sun look like a dying ember. These stellar heavyweights represent a different kind of cosmic extreme. Meet R136A1. A star that weighs over 200 times more than our Sun, but occupies a space only 30 times wider. This makes it incredibly dense compared to bloated giants like UY Scuti. If stars were people, UY Scuti would be a 7-foot-tall person weighing 100 pounds, while R13601 would be a bodybuilder packed with muscle. This massive star burns so hot that its surface temperature reaches over 50,000 degrees, 10 times hotter than our Sun. The intense heat gives R136A1 a brilliant blue-white color and makes it shine with the brightness of nearly 9 million suns. If you replaced our Sun with this stellar monster, Earth would be instantly vaporized by the intense radiation. The star's extreme mass creates crushing gravitational forces that compress the core to incredible densities and temperatures. Nuclear fusion proceeds at such a frantic pace that the star burns through its hydrogen fuel in just a few million years, a cosmic blink of an eye compared to our Sun's 10 billion year lifespan. R136A1 lives like it's running out of time, because it literally is. Located in the Tarantula Nebula, 160,000 light-years away, in the Large Magellanic Cloud, R136A1 sits in one of the most active, star-forming regions known to astronomy. The nebula glows with the combined light of thousands of hot, young stars, but R136A1 outshines them all. Its intense ultraviolet radiation ionizes gas across hundreds of light-years, creating a cosmic lighthouse visible from millions of light-years away. The star's powerful radiation also creates stellar winds moving at over 6 million miles per hour, fast enough to circle Earth in just 4 minutes. These winds carry away the star's outer layers at a rate of about 1 Earth mass every 1,000 years. The star is literally evaporating itself through the sheer intensity of its radiation, losing mass almost as fast as it can burn fuel. Stars this massive push the absolute limits of what stellar physics allows. Theoretical calculations suggest that stars much heavier than R136A1 would be torn apart by their own radiation pressure before they could finish forming. The star sits right at the edge of the possible, a cosmic extreme that challenges our understanding of how massive stars can grow. When R136A1 finally exhausts its fuel, the collapse will be so violent that it might skip the neutron star phase entirely and collapse directly into a black hole. The explosion will likely be a hypernova, visible from billions of light-years away, and possibly accompanied by a gamma-ray burst that could sterilize planets across the galaxy. But even this stellar heavyweight faces a challenger that burns with impossible brightness. Deep in space lurks a star so bright it violates everything astronomers thought they knew about stellar physics. Luminous, blue variable stars like Eta Carinae burn with such intensity that they should tear themselves apart, yet somehow they continue to exist. Eta Carinae shines with the brightness of over 4 million suns, making it one of the most luminous stars in the galaxy. But its brightness isn't constant. The star undergoes massive outbursts that can increase its light output by factors of 10 or more. During one eruption in the 1800s, it briefly became the second brightest star in the night sky, despite being over 7,000 light-years away. Think of Eta Carinae as a stellar time bomb with an unpredictable fuse. The star balances on a knife's edge between stability and destruction, constantly threatening to explode in one of the most powerful supernovas ever witnessed. Its extreme luminosity creates radiation pressure so intense that it should blow the star apart, yet the star's enormous mass provides enough gravity to hold it together, barely. The star's instability has created one of the most spectacular nebulae in the galaxy. The Homunculus Nebula, formed by material ejected during Eta Carinae's great eruption in the 1840s, resembles a cosmic hourglass glowing with the light of the central star. The nebula contains enough material to create 10 stars like our Sun, all of it blown away in a single violent outburst. But Eta Carinae harbors an even stranger secret. It's actually 2 stars locked in a deadly orbital dance. The primary star, a luminous blue variable, orbits with a slightly smaller but still massive companion every 5.5 years. When the 2 stars approach each other during their elliptical orbit, their powerful stellar winds collide, creating shock waves that generate X-rays and violent eruptions. The binary nature makes Eta Carinae even more dangerous. When massive binary stars reach the end of their lives, they can trigger some of the most energetic explosions in the universe. The 2 stars may eventually merge, creating a hypernova that could outshine the entire galaxy for months. Alternatively, one star might explode first, disrupting the orbit and causing the surviving star to spin rapidly, a recipe for generating gamma-ray bursts. Astronomers monitor Eta Carinae constantly because it represents one of the most likely candidates for the next galactic supernova. The star shows all the signs of being in its final stages, having already ejected much of its outer envelope in previous outbursts. When it finally explodes, the supernova will be visible from Earth even during the day, appearing as bright as the quarter moon. The star's location in the southern sky means it poses no direct threat to Earth. Any gamma-ray burst would point away from our solar system. But the explosion will still have dramatic effects, potentially triggering the formation of new stars throughout our region of the galaxy and adding to the cosmic ray flux that constantly bombards our planet. Eta Carinae proves that the universe still holds surprises that challenge our understanding of stellar physics. Some stars don't die alone. They feed on companions, growing fat on stolen matter until they explode with the force of 1,000 ordinary supernovas. These stellar vampires represent the ultimate expression of cosmic greed. Type 1. Supernovas begin with white dwarf stars, the compressed cores left behind when sun-like stars die. These stellar corpses are roughly the size of Earth, but contain as much mass as our Sun, creating surface gravity 60,000 times stronger than what we experience. Under normal circumstances, white dwarfs simply cool down over billions of years, fading to invisible black dwarfs. But when a white dwarf has a companion star, the story becomes far more dramatic. The white dwarf's intense gravity can steal material from its neighbor, pulling streams of hydrogen and helium onto its own surface. This stolen matter doesn't just sit there. It accumulates in a thin layer that grows denser and hotter as more material piles on top. Think of it like building a house of cards, but each card weighs as much as a mountain. Eventually, the stolen material reaches a critical point where the bottom layer becomes hot and dense enough for nuclear fusion to begin. But this isn't the controlled fusion that powers normal stars. It's a runaway thermonuclear explosion that engulfs the entire white dwarf in seconds. The explosion completely destroys the white dwarf, converting roughly half of its mass into pure energy, according to Einstein's famous equation. The amount of energy released equals what our Sun will produce over its entire 10 billion-year lifetime, but it all gets released in just a few seconds. The explosion creates temperatures of several billion degrees, hot enough to fuse silicon into iron and nickel in the expanding fireball. These thermonuclear supernovas shine with remarkable consistency, always reaching roughly the same peak brightness regardless of the white dwarf's original mass or the nature of its companion. This makes them incredibly valuable as standard candles for measuring cosmic distances. Astronomers use Type 1a supernovas to map the expansion of the universe and discover dark energy. The explosion creates roughly 1.5 times the mass of our Sun in radioactive nickel-56, which decays into cobalt-56 and then iron-56 over a period of months. This radioactive decay powers the supernova's afterglow, keeping it visible for nearly a year as it slowly fades from view. The iron created in these explosions makes up a significant fraction of all the iron in the universe. But some white dwarfs are even greedier than others. Superchandrasekhar supernovas occur when white dwarfs somehow grow beyond the theoretical mass limit that should cause them to collapse. These monsters can reach twice the normal mass limit before exploding, with energies that dwarf even normal Type 1a events. The most extreme stellar cannibals may be responsible for some of the brightest explosions ever observed. In the furthest reaches of space, astronomers have detected explosions so powerful they make ordinary supernovas look like fireflies. These superluminous supernovas challenge everything we thought we knew about stellar death. Imagine an explosion 100 times brighter than a normal supernova, shining with the light of 50 billion suns. These cosmic monsters can outshine their entire host galaxies for months, announcing their presence across billions of light-years of space. The first superluminous supernova discovered was so bright that astronomers initially thought they were looking at the explosion of an entire galaxy. The energy requirements for these explosions seem impossible to explain through normal stellar physics. A typical supernova converts about 1% of the star's mass into energy, but superluminous events appear to be far more efficient. Some may convert 10% or more of the progenitor star's mass into pure energy, approaching the theoretical limits of what matter can release. One theory suggests these explosions occur when the most massive stars in the universe, weighing more than 150 times our Sun, undergo pair instability supernovas. In the cores of these stellar giants, temperatures become so extreme that high-energy photons spontaneously convert into matter-antimatter pairs. This removes energy from the core, causing it to contract and heat up even further. The process creates a runaway reaction that tears the entire star apart in a thermonuclear explosion far more powerful than ordinary core collapse supernovas. Unlike normal supernovas that leave behind neutron stars or black holes, pair instability events completely destroy the progenitor star, converting most of its mass into energy and heavy elements that get scattered into space. These explosions may have been far more common in the early universe, when the first generation of stars formed from pure hydrogen and helium. Without heavy elements to help them cool during formation, these primordial giants could grow to sizes impossible in today's universe. Their deaths as superluminous supernovas would have enriched the early cosmos with the first heavy elements. Another type of superluminous supernova may be powered by rapidly spinning neutron stars called magnetars. These objects have magnetic fields trillions of times stronger than Earth's, and they can inject enormous amounts of energy into the expanding supernova debris. The magnetar acts like a cosmic generator, converting its rotational energy into electromagnetic radiation that powers the explosion's extreme brightness. Some superluminous supernovas show evidence of interaction with dense shells of material surrounding the progenitor star. The shockwave from the explosion slams into this pre-existing material, converting kinetic energy into light with remarkable efficiency. These interaction-powered events can remain bright for years instead of the typical months for ordinary supernovas. The most extreme examples may not be supernovas at all, but rather the tidal disruption of stars by supermassive black holes. When a star wanders too close to a black hole weighing millions of times our Sun's mass, tidal forces stretch it like taffy and tear it apart. The stellar debris forms an accretion disk around the black hole, releasing tremendous amounts of energy as it spirals inward. But even these cosmic monsters pale compared to the most energetic explosions in the universe. When the most massive stars die, They can focus their explosive energy into narrow jets that drill through space at nearly the speed of light. These cosmic blowtorches create the most powerful sustained explosions in the universe. Gamma ray bursts represent the universe's ultimate expression of concentrated destruction. In just 10 seconds, a single burst can release more energy than our sun will produce over its entire 10 billion year lifetime. But this energy doesn't spread out in all directions like an ordinary explosion. It gets focused into two narrow beams that concentrate the destructive power like cosmic laser pointers. The beams form when a rapidly rotating massive star collapses into a black hole. The star's angular momentum gets conserved during the collapse, creating a black hole spinning hundreds of times per second. This rotation, combined with the star's powerful magnetic field, creates a cosmic dynamo that channels matter and energy into relativistic jets shooting out from the black hole's poles. Think of it like the most powerful fire hose imaginable, but instead of water, it shoots high-energy particles and electromagnetic radiation at 99.9% the speed of light. The jets are so narrow that they span less than 1 degree of sky, meaning you have to be almost perfectly aligned with the beam to see the gamma ray burst at all. When astronomers detect a gamma ray burst, they're looking down the barrel of one of these cosmic guns from thousands or millions of light years away. The fact that we can see them at such vast distances proves just how incredibly powerful they must be. A gamma ray burst occurring in our galaxy would be like having a second sun appear in the sky, but one that emits deadly gamma rays instead of life-giving visible light. The jets don't just produce gamma rays. They also accelerate particles to energies far beyond anything achievable in human-built accelerators. These ultra-high-energy cosmic rays travel through the universe for billions of years, occasionally striking Earth's atmosphere and creating cascades of secondary particles. Some of the most energetic particles ever detected may have originated in gamma ray bursts billions of light years away. The jets can maintain their power for minutes or even hours, drilling through the stellar debris and pushing shockwaves through the surrounding interstellar medium. When the jets finally break through the surface of the exploding star, they create the gamma ray burst that announces the birth of a new black hole to the entire universe. But gamma ray bursts aren't just destructive. They're also creative. The intense radiation can trigger star formation in nearby molecular clouds, just like ordinary supernova shockwaves, but with far greater efficiency. The jets also produce and scatter heavy elements throughout their host galaxies, contributing to the chemical evolution that makes planets and life possible. Some gamma ray bursts may be pointed directly at Earth, hidden by the vast distances involved and the finite speed of light. The explosion that creates the burst we'll observe tomorrow may have occurred when complex life was first evolving on Earth billions of years ago. Yet even gamma ray bursts can't compare to the most energetic events in cosmic history. The most violent events since the Big Bang occur when two black holes, locked in a death spiral for millions of years, finally merge in a collision that shakes the very fabric of space and time. Imagine two objects, each weighing dozens of times more than our sun, compressed into spheres just a few miles across, orbiting each other at half the speed of light. As they spiral inward, they create ripples in space-time itself, gravitational waves that stretch and compress the universe like a cosmic accordion. The energy carried away by these waves causes the orbit to decay, pulling the black holes closer together in an accelerating dance of destruction. The final moments happen incredibly fast. When the black holes get within a few hundred miles of each other, they complete dozens of orbits per second, whipping around faster than helicopter blades. The gravitational waves they produce carry away the equivalent of several solar masses worth of energy every second. All of it converted from the orbital motion into distortions of space-time. The actual collision lasts less than 1 second, but in that brief moment, the two black holes release more energy in gravitational waves than all the stars in the observable universe produce in electromagnetic radiation. It's like converting 3 times the mass of our sun directly into energy, but instead of light and heat, that energy gets released as ripples in the geometry of the universe itself. The merger creates a single, larger black hole that initially vibrates like a struck bell, ringing down as it settles into its final configuration. These ring-down gravitational waves carry information about the new black hole's mass and spin, allowing astronomers to study the properties of objects that don't emit any light at all. When these gravitational waves finally reach Earth after traveling for billions of years, they compress and stretch space by amounts smaller than 1/10,000th the width of a proton. Detecting such tiny distortions requires the most sensitive instruments ever built, laser interferometers with arms several miles long that can measure changes in distance smaller than any other measurement in the history of science. The discovery of gravitational waves from black hole mergers has opened an entirely new window on the universe. Before, astronomers could only study objects that emit or absorb electromagnetic radiation. Now, they can detect events that produce no light at all, revealing a hidden population of black holes throughout the cosmos. Some black hole mergers occur in dense stellar environments where the collision also produces electromagnetic radiation. When the merging black holes have accretion disks or nearby stars, the gravitational waves can trigger outbursts of X-rays and gamma rays that make the event visible to traditional telescopes as well. The rate of black hole mergers throughout the universe tells us about the lives and deaths of the most massive stars. Every merger represents two stars that lived, evolved, and died as supernovas or hypernovas billions of years ago. The black holes they left behind wandered through space for eons before finally finding each other and spiraling to their ultimate fate. But black holes aren't the only objects that can merge in cosmic collisions. When two neutron stars collide, they create an explosion that produces more gold than exists in Earth's entire crust. These kilonova events are the universe's primary factories for the heaviest elements in the periodic table. Neutron stars are the densest objects in the universe that aren't black holes, city-sized spheres containing more mass than our sun, where matter is crushed to densities that defy imagination. When two of these cosmic monsters spiral together and collide, they create conditions more extreme than anything that occurs during ordinary stellar evolution. The collision happens at roughly 30,000 miles per second, with each neutron star weighing about 1.5 times as much as our sun. The impact releases more energy than a typical supernova. But the real magic happens in the debris ejected during the merger. The incredibly neutron-rich material undergoes rapid neutron capture, building up atomic nuclei far heavier than iron. Think of it like cosmic alchemy, where the collision literally transmutes elements from one form to another. In just a few seconds, the kilonova creates more gold, platinum, and uranium than billions of ordinary stars could produce over their entire lifetimes. The collision that astronomers observed in 2017 probably created about 10 Earth masses worth of gold, roughly 100 times more gold than exists in our planet's crust. The process works because neutron star matter contains far more neutrons than normal atomic nuclei. When this material gets ejected at high speeds during the collision, the excess neutrons stick to existing atomic nuclei faster than they can decay. This rapid neutron capture, called the R process, can build up elements as heavy as uranium and beyond within seconds. The expanding debris cloud glows with a distinctive reddish light as the newly created heavy elements decay radioactively. The kilonova starts out blue-white from the initial shock heating, but quickly shifts to red as the radioactive decay of unstable nuclei dominates the light output. This characteristic color signature allows astronomers to identify kilonova events even from billions of light years away. The collision also produces a brief gamma-ray burst as matter falls into the black hole created by the merger. But unlike the long gamma-ray bursts produced by hypernova explosions, kilonova bursts last only a few seconds and are much less energetic. The real show comes from the radioactive glow that can be detected for weeks after the initial collision. Kilonova events are incredibly rare. Astronomers estimate they occur only once every 10,000 years in a typical galaxy. But they're so efficient at producing heavy elements that they may be responsible for creating most of the gold, platinum, and uranium in the universe. Every piece of jewelry containing these precious metals contains atoms forged in neutron star collisions billions of years ago. The gravitational waves from the collision travel at the speed of light, arriving at Earth just seconds before the electromagnetic radiation from the explosion. This tiny time delay allows astronomers to triangulate the position of the kilonova and study it with multiple telescopes across the electromagnetic spectrum. But these cosmic catastrophes also reveal something profound about the nature of matter itself. Extreme stellar environments create natural laboratories where the fundamental laws of physics get pushed to their absolute limits. These cosmic experiments test our theories in ways no earthly laboratory ever could. Einstein's theory of general relativity makes specific predictions about how matter and energy behave under the most extreme conditions imaginable. Near black holes and neutron stars, space and time become so warped that clocks run slower, light bends along curved paths, and the very geometry of the universe becomes twisted. These effects, barely detectable in Earth's weak gravitational field, become dominant forces in the vicinity of collapsed stars. The surface of a neutron star experiences gravitational time dilation so extreme that a clock there would run about 30% slower than a clock on Earth. This isn't just theoretical. Astronomers can measure the effect by studying the light emitted from the neutron star's surface. The gravitational redshift stretches the wavelengths of photons climbing out of the star's intense gravitational well. Near the event horizon of a black hole, time dilation becomes even more extreme. An astronaut falling toward the black hole would experience time normally, but observers far away would see the astronauts' clocks running slower and slower as they approach the point of no return. At the event horizon itself, time appears to stop completely from the perspective of distant observers. Black holes also create gravitational lensing effects that act like cosmic telescopes. The intense gravity bends light rays from background objects, creating multiple distorted images of the same star or galaxy. Some black holes can focus light so efficiently that they make distant objects appear brighter than they would without the lensing effect. The magnetic fields around neutron stars reach strengths trillions of times more powerful than anything achievable on Earth. These fields are so intense that they affect the very structure of atoms, stretching electron orbitals into needle-like shapes and splitting spectral lines in ways that would be impossible under normal conditions. The magnetic field essentially rewrites the rules of atomic physics. When matter falls into a black hole or neutron star, it gets accelerated to significant fractions of light speed. These relativistic effects cause the infalling material to emit high-energy radiation across the electromagnetic spectrum. The resulting X-ray and gamma-ray emissions provide direct observational evidence for Einstein's predictions about extreme gravity. Gravitational waves from merging black holes and neutron stars offer perhaps the most dramatic confirmation of general relativity. The wave patterns detected by laser interferometers match Einstein's equations with incredible precision, validating predictions made over a century ago, using nothing but pure mathematics. The jets produced by rotating black holes demonstrate how extreme rotation can extract energy from the gravitational field itself. The Penrose process allows matter falling into the ergosphere around a spinning black hole to emerge with more energy than it started with, powered by the black hole's rotational energy. These natural laboratories also probe the fundamental nature of matter under conditions that cannot be recreated anywhere else. Inside neutron stars, matter exists in states so exotic that they challenge our understanding of what atoms can become. These stellar remnants contain phases of matter that may not exist anywhere else in the modern universe. The outer crust of a neutron star resembles a crystalline solid, but one made of atomic nuclei packed together like marbles in a jar. The nuclei are so tightly squeezed that they form a perfect crystal lattice, harder than diamond, yet under pressures that would instantly crush any material found on Earth. The electrons that normally orbit these nuclei instead form a degenerate gas that fills the space between the crystalline lattice points. Deeper inside the neutron star, the atomic nuclei begin to merge together, creating increasingly neutron-rich isotopes that cannot exist under normal conditions. The boundary between individual nuclei starts to blur as they melt together into bizarre shapes that physicists call nuclear pasta, structures that resemble lasagna sheets, spaghetti strands, and gnocchi depending on the density and pressure. At the very center of the most massive neutron stars, the pressure may become so extreme that neutrons themselves break down into their component quarks. This creates a state of matter called quark soup. where the fundamental building blocks of protons and neutrons exist as a free liquid. Some theoretical physicists think this quark matter might be the true ground state of all matter in the universe. The transition from normal matter to quark matter may occur suddenly, like water freezing into ice. If this phase transition happens inside a neutron star, it could release tremendous amounts of energy and completely change the star's structure. Some gamma-ray bursts and other high-energy astrophysical phenomena might be caused by neutron stars undergoing sudden phase transitions in their cores. Even stranger possibilities exist at the highest densities. Exotic forms of matter involving strange quarks, kaons, or other particles from high-energy physics might exist in neutron star cores. These phases of matter would have properties completely unlike anything in our everyday experience, potentially including superconductivity, superfluidity, or other quantum phenomena on macroscopic scales. The magnetic fields in neutron stars are so intense that they affect the vacuum of space itself. In these extreme environments, empty space becomes birefringent, splitting light into two polarization states that travel at slightly different speeds. The quantum vacuum becomes an active medium that can scatter and absorb electromagnetic radiation. Some neutron stars may contain regions where the strong nuclear force becomes attractive instead of repulsive, creating hyperon matter containing particles that don't exist in ordinary atoms. These exotic particles would make the neutron star even more compact, potentially pushing it closer to the mass limit where it would collapse into a black hole. The equation of state, the relationship between pressure and density inside neutron stars, remains one of the biggest unsolved problems in physics. Different theories predict vastly different internal structures, and only precise measurements of neutron star masses and radii can determine which models are correct. Yet even these exotic states of matter may be temporary waypoints on the path to something even stranger. Just 640 light-years from Earth sits a red supergiant that could explode at any moment, creating the most spectacular light show in human history. Betelgeuse has already begun its final death spiral. Betelgeuse dominates the constellation Orion, shining as the bright red star that marks the giant hunter's shoulder. But this stellar giant is living on borrowed time. The star has already exhausted the hydrogen fuel in its core and has begun fusing heavier elements in a desperate attempt to stave off gravitational collapse. Every element it burns brings it one step closer to the iron core that will trigger its explosive death. The star varies dramatically in brightness over periods of months and years, pulsing like a cosmic heartbeat as it struggles to maintain equilibrium between gravity and radiation pressure. Sometimes Betelgeuse dims so much that it drops out of the list of the 20 brightest stars in the sky. Other times it brightens to rival the blue giant Rigel on the opposite side of Orion. These brightness variations signal the star's internal instability. Betelgeuse has begun ejecting massive amounts of material from its surface, creating a complex nebula of gas and dust that surrounds the star for light years in every direction. The star is essentially blowing itself apart in slow motion, losing mass at a rate equivalent to Earth's mass every 6,000 years. High-resolution images reveal that Betelgeuse's surface is far from uniform. Massive convection cells create hot spots in cool regions across the star's photosphere, like bubbles rising in a pot of boiling water. These convective motions transport energy from the nuclear furnace in the core to the surface, but they also create the instabilities that drive the star's brightness variations. The star's enormous size makes it one of the few stars other than our Sun whose surface features can be directly observed. Betelgeuse is so large that if it replaced our Sun, its surface would extend past the orbit of Mars. The star's diameter changes significantly as it pulses, expanding and contracting by amounts larger than Earth's orbit around the Sun. When Betelgeuse finally explodes as a supernova, it will become the brightest star in Earth's sky since humans began keeping written records. The explosion will be visible during the day, appearing as bright as the quarter moon and casting shadows on Earth's surface. The supernova will remain visible to the naked eye for over a year, slowly fading as the radioactive elements created in the explosion decay. The supernova poses no direct threat to Earth. The distance is too great for the radiation to cause significant damage to our atmosphere or biosphere. but the explosion will have profound effects on human civilization, appearing as a brilliant new star that outshines Venus and challenges the Moon for dominance of the night sky. Astronomers around the world monitor Betelgeuse constantly, watching for the telltale signs that might indicate the star is about to explode. The supernova could occur tomorrow, or it might not happen for another 100,000 years. From our perspective, the star exists in a state of cosmic suspense, balanced on the knife's edge between stability and catastrophic collapse. But Betelgeuse represents just one example of the stellar violence that surrounds us. Within 50 light-years of Earth lurk dozens of stellar time bombs that could affect our planet when they explode. Most of these threats remain hidden from casual observers, invisible to the naked eye but closely monitored by astronomers. The danger zone for supernova effects extends roughly 50 to 100 light-years from Earth, depending on the type of explosion and the orientation of any gamma-ray jets. Within this cosmic sphere of concern, astronomers have identified several dozen stars massive enough to explode as supernovas within the next few million years. Most of these stellar giants are too faint or too obscured by interstellar dust to be visible without telescopes. IK Pegasi, located just 150 light-years away, represents one of the closest supernova candidates to Earth. This system contains a white dwarf star that's stealing material from a companion, gradually growing toward the mass limit that will trigger a thermonuclear explosion. When it finally explodes as a Type 1a supernova, IK Pegasi will briefly outshine every other star in the night sky. The explosion would bathe Earth in ultraviolet and X-ray radiation intense enough to damage our ozone layer, potentially leading to increased cancer rates and disruption of marine ecosystems. The radiation would arrive at Earth traveling at the speed of light, giving no advance warning before the assault on our atmosphere begins. Wolf-Rayet stars represent another class of nearby threats. These extremely hot, massive stars have already lost their outer hydrogen layers, exposing the nuclear burning core directly to space. They burn so intensely that they blow away their remaining mass in powerful stellar winds, creating beautiful but ominous nebulae around themselves. When Wolf-Rayet stars explode, they often produce gamma-ray bursts that could be devastating if pointed toward Earth. The binary system WR104, located about 8,000 light-years away, contains a Wolf-Rayet star that's rotating rapidly enough to potentially produce a gamma-ray burst when it explodes. Although the distance provides some protection, a nearby gamma-ray burst could still strip away Earth's ozone layer and trigger a mass extinction event. Even more concerning are the runaway stars that have been ejected from their birth clusters and now race through space at high speeds. Some of these stellar refugees may pass close to our solar system in the future, bringing their supernova threat much closer to Earth than their current distances would suggest. The good news is that none of the known supernova candidates in our local neighborhood show signs of imminent explosion. Most are likely still millions of years away from their final fate, giving life on Earth plenty of time to evolve and adapt. But the universe contains many stellar time bombs that remain undiscovered, hidden behind dust clouds, or simply too faint for our current surveys to detect. Our galaxy experiences roughly one supernova every 50 years on average, meaning that dozens of massive stars have exploded within a few thousand light-years of Earth during human history. The fact that we've survived this long suggests that our solar system occupies a relatively quiet region of the galaxy, protected by chance from the worst effects of stellar violence. But this cosmic peace cannot last forever. Every supernova explosion contributes to a vast cosmic recycling program that has been operating for over 13 billion years, gradually enriching the galaxy with the heavy elements necessary for planets and life. When the universe was young, it contained only hydrogen and helium created during the Big Bang. The first generation of stars formed from this pristine material, burning their nuclear fuel and creating heavier elements in their cores. But these elements remained locked inside the stars until the massive ones exploded as supernovas, scattering their nuclear ashes into space. Each successive generation of stars formed from material slightly enriched with heavy elements from previous stellar explosions. The process is incredibly slow. It takes billions of years for the galaxy's overall composition to change significantly. But the cumulative effect has been dramatic, increasing the abundance of elements like carbon, oxygen, and iron by factors of thousands since the early universe. The Sun formed roughly 4.5 billion years ago from a molecular cloud that had already been enriched by billions of years of stellar evolution. The heavy elements in that cloud allowed the formation of rocky planets like Earth, where complex chemistry and eventually life could develop. We literally exist because of the nuclear ashes from countless stellar explosions that occurred before our solar system formed. Different types of supernovas contribute different elements to this cosmic recycling program. Core collapse supernovas from massive stars produce most of the oxygen, silicon, and other elements between carbon and iron in the periodic table. Type 1a thermonuclear supernovas create most of the iron peak elements that form the cores of rocky planets and the hemoglobin in our blood. The heaviest elements beyond iron come primarily from neutron star mergers and the most energetic supernova explosions. The gold in jewelry, the silver in electronics, the uranium in nuclear reactors, all of these elements were forged in cosmic catastrophes far more violent than ordinary stellar evolution. Every atom of these precious metals represents a piece of cosmic history stretching back billions of years. The recycling program isn't uniformly distributed throughout the galaxy. Regions with active star formation get enriched more rapidly, while the outer edges of galactic disks remain relatively pristine. The metallicity gradient, the variation in heavy element abundance across the galaxy, provides clues about how the Milky Way formed and evolved over cosmic time. Supernova explosions also regulate the rate of future star formation by heating and dispersing the interstellar medium. Too many explosions can blow away the gas needed for new stars to form, creating a negative feedback loop that prevents runaway star formation. This self-regulation helps explain why galaxies don't consume all their gas in a single burst of stellar birth. The expanding bubbles created by supernova remnants create a complex, frothy structure in the interstellar medium. Our solar system currently sits inside one of these ancient supernova bubbles, surrounded by hot, thin gas that was heated by stellar explosions millions of years ago. We're literally living inside the aftermath of cosmic violence. As UY Scuti and other massive stars continue their evolution toward explosive death, they will add their own contributions to this galactic recycling program. Across the Milky Way, massive stars follow a predictable assembly line of destruction, each stage bringing them closer to the violent explosions that will scatter their contents across the galaxy. The process begins in stellar nurseries, vast molecular clouds where gravity slowly pulls together enough material to ignite nuclear fusion. The most massive stars form quickly, sometimes reaching their full size in less than 1 million years. These stellar giants immediately begin burning through their fuel at prodigious rates, living their entire lives in the cosmic fast lane. Young massive stars shine with brilliant blue-white light, their surfaces heated to temperatures of 30,000 degrees or more. They blast powerful stellar winds into space, clearing out cavities in the surrounding gas and dust. These stellar winds carry away a significant fraction of the star's mass, setting the stage for the exotic phases of evolution that will follow. As the star ages and exhausts its core hydrogen, it begins the transition to a red supergiant phase. The core contracts and heats up while the outer layers expand dramatically, creating the enormous sizes we see in stars like UY Scuti and Betelgeuse. This red supergiant phase represents the beginning of the end. The star has entered its final million years of life. The internal structure becomes increasingly complex as the star burns through successive layers of nuclear fuel. Hydrogen burns in a shell around a helium core, which eventually ignites to burn carbon and oxygen. Each new fuel source burns hotter and faster than the last, creating a nested series of nuclear furnaces that will eventually produce elements all the way up to iron. Some massive stars experience dramatic mass loss episodes during this phase, ejecting spectacular nebulae that become visible as glowing shells of gas around the central star. The homunculus nebula around Eta Carinae and the complex structures around other luminous blue variables show how violent this pre-supernova phase can become. The final moments arrive when silicon fusion in the core produces iron. Nuclear fusion stops abruptly, and gravity wins its billion-year battle in less than 1 second. The core collapse triggers the supernova explosion that tears the star apart and scatters its nuclear ashes into the surrounding space. But the assembly line doesn't end with the explosion. The expanding supernova remnant continues to evolve for hundreds of thousands of years, gradually mixing with the interstellar medium and contributing to the next generation of star formation. The neutron stars, or black holes, left behind continue to affect their surroundings through magnetic fields, gravitational effects, and occasional outbursts. This cosmic assembly line operates continuously throughout the galaxy, with new massive stars constantly forming, while others progress through each stage of evolution toward their explosive fate. At any given moment, the Milky Way contains stars at every phase of this process, from newborn giants just beginning to burn hydrogen to ancient supergiants on the verge of collapse. The predictable nature of stellar evolution allows astronomers to identify which stars will explode next and roughly when those explosions might occur. Stars like UY Scuti, Betelgeuse, and Eta Carinae have all reached the red supergiant phase, placing them in the final stretch of the cosmic assembly line. But even after billions of years of stellar evolution, the universe still holds surprises. UY Scuti's story will end in one of the most spectacular explosions our galaxy has ever witnessed, but the exact details of its death remain shrouded in cosmic uncertainty. The star has already begun its final countdown, burning through nuclear fuel at a rate that would power our sun for millions of years. Deep in UY Scuti's core, silicon fusion proceeds frantically, creating iron peak elements that cannot be burned for additional energy. When the core fills with iron, nuclear fusion will stop completely, and gravity will finally win its billion-year battle against radiation pressure. The core collapse will happen faster than sound can travel through the star. In less than 1 second, a region larger than Earth will compress down to a sphere just 12 miles across, creating the densest matter in the known universe. The rebound from this collapse will generate a shockwave carrying more energy than our sun will produce in its entire lifetime. If UY Scuti's core weighs less than about 3 times our sun's mass, the shockwave will succeed in exploding the star and leave behind a neutron star spinning hundreds of times per second. This cosmic lighthouse will beam radio pulses across the galaxy for millions of years, announcing the death of the largest known star to any civilizations capable of detecting them. But if the core is more massive, not even neutron degeneracy pressure can stop the final collapse. The core will continue shrinking past the neutron star stage, eventually forming a black hole that could weigh dozens of times more than our sun. The event horizon will swallow the core's light forever, creating a cosmic graveyard where space and time themselves become distorted. The most dramatic possibility involves UY Scuti's rotation. If the star spins rapidly during its collapse, the resulting black hole could generate relativistic jets that punch through the stellar debris at nearly light speed. These jets would create a hypernova explosion visible from other galaxies, possibly accompanied by a gamma-ray burst that would briefly outshine the entire Milky Way. Regardless of the exact mechanism, UY Scuti's explosion will scatter approximately 25 times the mass of our sun into the surrounding space. This debris will contain all the elements forged during the star's lifetime: carbon from helium burning, oxygen from carbon fusion, silicon from oxygen burning, and iron from the final stages of nuclear evolution. The expanding shockwave will trigger star formation in nearby molecular clouds, ensuring that UY Scuti's death leads to the birth of new stellar generations. Some of these future stars will have planets, and some of those planets may develop life using the very elements scattered by UY Scuti's explosion. The supernova will remain visible from Earth for over a year, appearing as a brilliant new star in the constellation Scutum. Ancient civilizations would have recorded it as a portent or divine message, unaware that they were witnessing the final moments of a star 1,700 times larger than their own sun. In the end, UY Scuti's legacy will be measured not by its record-breaking size, but by its contribution to the ongoing cycle of stellar death and rebirth that has enriched our galaxy for over 13 billion years. The largest star we know will live on as countless atoms scattered throughout space, carrying the potential for future worlds among the stars. The universe continues to create even larger stellar monsters in distant galaxies, ensuring that UY Scuti's size record will eventually be broken. But for now, this red supergiant reigns supreme, a cosmic giant whose violent death will light up the galaxy and seed the cosmos with the elements of life itself.